All right, guys, let's talk about number one. So we'll go through all of the options and talk about why it's right or wrong. So let's start with the first one. It says the entropy of the reactants exceeds that of the product. So for this, we didn't really talk about it in class, but everybody is doing their reading, so you should know what entropy is. Entropy is a fancy word for randomness. Okay, so basically the question is saying the randomness of the reactants exceeds that of the products. Now, to determine this, we need to look at how many moles of chemicals we have on the left and right side. So if we take a look, how many moles of stuff do we have here? 2. But typically we look at just the gases because gases are the ones that's super random, right? They're the ones flying around. So we can just write 1 mole of gas here. But if you take a look at the right side of the reaction, the product side, how many moles of gas are there? 5, yeah. There's 5 moles of gas. So which one will be more random? The one with 1 mole or 5 moles? Yeah, 5. So the product side is going to be more random. So this answer is incorrect because the entropy will be greater on the product side, not the reactant side. So I know all the other problems we did earlier were all AAA, but now it's not A. All right, let's go to part B. It says H2O will always be the limiting reagent. Now, we know from just our basic stoic knowledge that this is not true. You can't always have something as a limiting reagent. If I added 1 billion gallons of water, that's not going to be the limiting reagent. So this is not correct. All right, this reaction is never thermodynamically favored. Basically, this means that this reaction, it's not going to want to go forward. However, if you take a look at the enthalpy value, what do you notice about it? Yeah, it's negative, which means there are instances this wants to be thermodynamically favored, and so C is not. So the answer will be D, and it makes sense because it is an exothermic reaction. It's going to release energy. If energy is released, the temperature of the surroundings will get greater. Again, easiest way to think about this is if something is delta H is negative, you could think of an explosion or like a hand warmer. The surroundings get hotter, higher temperature. All right, let's go to number 2, and I believe this one, I ripped it off one of the previous AP exams. So this is about the level of question you will see on the AP exam. This is thermal chem. I'm going to give you guys about 3-4 minutes. See if you guys can do part A and part B on your own. This is going to require calculations. What's up? All right, so this question, we are doing some calorimetry stuff. So let's kind of go through the scenario, and then I'll explain how to solve parts A and B. So basically, it's saying that you got a can filled with water, and you are lighting a fire underneath it. You got some butane. And it tells you that there is 100 milliliters of water inside of this can. Okay, so 100 mils of water. And then it tells you the temperature increases from 25 to 82.3 degrees Celsius. So that's going to give you your TI. Your TI is 25 degrees Celsius, initial temperature. And your TF, your final temperature, is 82.3 degrees Celsius. And then it tells you the mass of butane that you burned. So you're burning some butane. And the mass of butane that you burned is 0.51 grams. We know the specific heat of water is just a given. And then the density of water is 1 gram per milliliter. Basically, what that allows us to do is convert the milliliters into 100 grams of water. Okay. And then it gives you the balanced equation for the butane's combustion. And then the question is asking how much heat did the water gain. So assuming all of the heat that was generated by the butane burning went into the water, that's what we're going to use. So we are going to use the Q equals MCAT equation because Q is heat. So we're calculating for heat. We're trying to find how much heat the water absorbed for the temperature to go up this much. So it's pretty simple. Once you identify the equation and what all the numbers mean, it's just plug and chug. So let's start with the mass. What is the mass of water? Yeah, 100 grams. So the mass of water is 100 grams. C stands for specific heat. What's the specific heat of water?
Is 4.1 4.18.
Correct. 4.18 is given to us right here. Joules per gram degrees Celsius. And then we have delta T, the change in temperature. That's final temperature minus initial temperature. So 82.3 degrees Celsius minus 25 degrees Celsius. Now, you do not need to convert to Kelvin because we're looking for the change. So whether you do Kelvin or Celsius, it's going to be the same. So let me give you guys about a minute, see if you guys can solve this, calculate this, and try to get the correct unit of measurement. You're trying to find heat, so what's your unit of measurement going to be? So go ahead, take a minute, calculate. We'll go over it, and then we'll use that answer for part B. All right, guys, so let's start calculating. So let's start with the change in temperature, just to make things easier for us. So we got 82.3 minus 25, and so inside of your parentheses, you are going to get 57.3 degrees Celsius. That is the delta T. And that works because this degree Celsius cancels out here, grams cancels out here. You're looking for joules, which makes sense because you're looking for energy. You're looking for heat, which is calculated in joules. So it's 57.3 times 100 times 4.18, and then this is going to be your answer in joules. Okay, everybody good? Okay, 23,951.4 joules. Okay, so that is how much heat the water gained. All right, it gets a little bit tricky for part B because this one you have to think a little bit creatively with your dimensional analysis. For part B, it's asking what is the experimentally determined heat of combustion of butane based on this experiment. So basically, how much energy did this reaction, this butane burning, release? But we have to do it in kilojoules per mole. Now, if we think about it, the amount of energy the water absorbed is the same amount of energy that the butane released, right? So that means the butane released the same number as part A, 23,951.4 joules. So that could be our answer, but they specifically ask in kilojoules per mole, and this is where it gets a little bit tricky. All right, now the first thing you want to do is you want to convert joules into kilojoules, right? Now that part's pretty easy. We just need to divide by 1,000 basically. 1,000 joules is 1 kilojoule. So that part works out pretty easily. Okay, but the part that's not easy is the part where it's moles on the bottom of the fraction. We need to get moles on the bottom of the fraction somehow, but we need to put something on the top of the fraction as well in order to convert it. And so this is where the creative thinking kind of comes in. So it tells us that the water absorbed this much energy, but in order to do that, what did we have to do? We had to burn some butane, right? And so it is 23,951.4 joules per 0.51 grams of butane. So it's per 0.51 grams of butane. Okay, so because in the experiment you burned this much butane and you got this much energy, it is this much energy per grams of butane. And from there, we can do grams per mole. We just need to look up the grams per mole of butane, and then we can solve from there. I'm just going to give you guys the number for it. Butane is 58.12 grams per mole. You could very easily calculate it using the molar mass right here. All right, let me give you guys about a minute, see if you guys can plug into your calculators and calculate for your final answer. Again, add the correct units of measurement. All right, guys, should have got about 2,729.52 kilojoules per mole. Okay, so moving on, let's take a look at part C, okay? So for part C, it's giving you the density of butane at 25 degrees Celsius, and then it's asking you how much heat would be emitted if 5 milliliters of butane was combusted. Okay, so for this one, I'm going to give you guys some time to try to think about it, figure out the dimensional analysis. I'll just let you guys know right now, you'll have to use your answer from part B in order to solve this. That gives you one of the conversion factors, so see if you guys can try part C on your own. Okay, again, you're going to have to use your answer from part B. All right, so for part C, first thing we're going to have to do is we're going to take our 5 mils of butane. So we're going to write down that as our starting value. And then we're going to, obviously, to convert it to grams, I think the density is probably a good giveaway. We're going to convert milliliters to grams. So we're going to set up our conversion factor, 1 milliliter per 0.573 grams of butane. All right. Next thing we're going to do is we're going to convert grams of butane into moles. Okay, that was the trick here. And then we had it in the previous problem or previous part. We're going to do 58.12 grams per 1 mole. Okay. Now, the reason why we want to convert it to moles is because if you remember from part B, our final answer was given in terms of moles and kilojoules. And our answer was 2,729.52 kilojoules. And this is perfect because the question is asking us for how much heat would be emitted. Heat is energy, and that's kilojoules. So this was the conversion factor setup. Okay, convert mils into grams using density. Then you convert it to moles using the molar mass. And then you use your answer from the previous part to find this right here. So if we plug it into our calculator, we got 5 times 0.573 divided by 58.12 times 2729.52. And that'll give us our answer. But again, make sure you're careful with the unit of measurement. It'll be 134.55 kilojoules. And that's going to be our final answer. Okay.